Welcome to Physics Unraveled. My name is Maddie. I know, we're the same person. Well, Maddie, I'm your image. Exactly.
We're here to talk about ray tracing. Now, what is ray tracing? Well, it's how we predict the location of an image. We know that light travels in straight lines, so that means when you do ray tracing, you must use a ruler. Let's say you shine a flashlight into a mirror. The light goes straight into the mirror, and the angle at which it touches the mirror, or the angle of incidence, is the angle at which it will reflect off the mirror, or the angle of reflection. It's also important to note that we measure these angles from a line perpendicular to the mirror. But how do we find where the image is located? Well, that's where ray tracing comes in. You draw lines from the angles of incidence back beyond the mirror, and the image will be located where the two lines of sight cross. However, observers tend to believe that the light came from a point along their sight line.
What happens when you look in a curved mirror? Does it form an enlarged or reduced image? Is it right side up or upside down? When close up, the concave mirror enlarges the image, but when far away, it flips the image upside down. Therefore, your distance from the mirror determines what the image will look like. Some important things to remember for ray tracing with concave mirrors are that the focal length is half the radius of curvature of the concave spherical mirror. Also, there are three rays that are used to form the images. Each image is located where two rays cross, or in some cases, appear to cross. There are certain characteristics an image that is formed by a concave mirror can have. It could be real or virtual, erect or inverted, enlarged, the same, or reduced. With a curved mirror, the F is the focal point, the C is the center, and the F is half the distance of C. Both the focal point and the center point lie on the principal axis. The first line will be parallel to the principal axis and will reflect through F. The second line will go through the focal point and reflect parallel, while the third line will go through C and reflect straight back. Just like with normal ray tracing, the image will appear where the two lines of sight cross. For the image to be real, you must be able to capture it on a screen or film at the image location. But what about ray tracing for convex lenses?
Well, Janice, I'm glad you asked. Think about it this way. If you look into a magnifying glass to read, the letters get bigger, but are slightly distorted. That's how convex lens images work. A convex lens will focus incoming parallel rays from a distant point, like an object, to a focal point. With convex lens tracing, you must put a focal point equidistant to the center of the lens. The first line you will draw will go parallel to the principal axis. It goes to the center of the lens, then goes through the back of the lens through the focal point. The second ray goes straight through where the center of the lens meets the principal axis, and is a straight shot from there. The third ray travels from the focal point to the center of the lens, and then travels parallel to the principal axis. The point where all three lines will meet will be the tip of your new image. From here, you can tell if the image is real or virtual, erect or inverted, enlarged, the same, or reduced. And that's all you really need to know about ray tracing. Now, you go out there and have some fun physics adventures. But remember, after you're done, to always shout, "Hooray!" Oh, hush, like you would have come up with anything better. Bet you won't be able to find me. Darn it.